What do we do when we have molecules? And so let's just summarize them. And so for the atomic orbitals, we have the unhybridized orbitals. Tell me what the unhybridized orbitals are. Yeah, S, P, D, etc. And then we have the hybridized atomic orbitals. And so what are the hybridized atomic orbitals that you should know? SP, SP2, SP3, SP3D, and SP3D2. Actually, there's etc. here. I'm not going to put because we have, different levels of hybridization. So for example, it's like, is it ionic or is it covalent? Well, there are different levels. It's not like 100% one or 100% the other. It's a lot less black and white and more gray. Right? And how many shades of gray are there? Well, it's a continuous range of grays. Well, the same thing here. It's not all like this. They're different percentages. So here it jumps from 50-50 to 1/3, 2/3. Well, actually, there's different levels here. Well, as far as percent P character, percent S character goes, just like percent ionic and percent covalent. Okay. And so this is why I say etc. here. But here we just mean the F orbitals, the G orbitals, etc. Now, what do we do when we have molecules? We got to make bonds. And so when we got molecules, so we got to make bonds. There are two ways that we're going to use these atomic orbitals. One way is we're going to look at molecules in terms of valence bond theory. And so in valence bond theory, a bond is equal to the overlap of atomic orbitals. And so let's pick some easy ones, like a 1s and a 1s. And so I have a 1s on hydrogen and another 1s on hydrogen, so just from the HH molecule, the H2 molecule. And the reason this overlap works is because in the overlap region here, there's a higher probability, right? Because now we got the higher probability of finding electron density in the overlap region. If there's a higher probability here in the overlap region, that means that there's going to be a net attraction between the nuclei. This is the diagram I had the other day. The net attraction of the nuclei towards each other, not really towards each other, but towards this higher concentration of electron density there. And so in valence bond theory, what we do is we take the atomic orbitals and just overlap them. This is the quantum mechanics light version. We're still using orbitals. Or we could apply molecular orbital theory. Molecular orbital theory is much more powerful. With valence bond theory, we sometimes get the wrong answer. And not only that, we can't make predictions. Like, for example, if I want to know the spectrum of a molecule, versus like the spectrum of an atom. If I take a hydrogen atom, measure its spectrum, and we can make predictions using quantum mechanics. We expect the same for molecules. If I take a molecule, I expect to determine its spectrum based on quantum mechanics, which we can using molecular orbital theory. We can do that. However, valence bond theory won't work. Valence bond theory is too overly simplified to give us energy levels with electrons. And so valence bond theory sometimes gives us the wrong answer, and sometimes we just can't attain certain types of information. MO theory should give us the correct answer, and we can get the spectral information from MO theory. So this is much more powerful. Much more powerful. And what we do here is we take an s orbital and an s orbital, one s and a one s. This is on a hydrogen atom and a hydrogen atom. And then we do something called an LCAO, linear combination of atomic orbitals. And we generate new orbitals. These are molecular orbitals. And so you just learned a whole bunch of atomic orbitals. Pretty soon you're going to learn a whole bunch of molecular orbitals in addition to the atomic orbitals you just learned. And some of these molecular orbitals would be like the sigma 1s orbital and the sigma star 1s orbital. This one's called an anti-bonding orbital. Because if there's electron density here, take a look at the nuclei. The nuclei see each other. The nuclei are going to repel each other. So here, in an anti-bonding orbital, nuclei repel. But if there's electron density in a bonding orbital, then the electron density is between the nuclei, and the nuclei will be attracted to that, and that's what creates the bond here. And so let's put in some electron density here. So we see the negative charge, we'll call the internuclear region. This is anti-bonding. And so what is a bond equal to in molecular orbital theory? I might as well talk briefly about that now. A bond equals greater electron density in bonding orbitals versus anti-bonding. That is, more electron density in bonding orbitals versus anti-bonding. If we have equal, then what happens is we have an attraction here that's canceled out by repulsion there, and we get no bond formation. And so we need greater electron density in bonding versus anti-bonding orbitals. Much more powerful, but there is a price. Here, valence bond, this is limited. Limited and can be wrong. The price you have to pay is it's a heck of a lot harder. Valence bond theory is easy compared to molecular orbital theory. It's easy. It's not easy learning it the first time, of course, but when you try to learn both, valence bond and MO, then for sure valence bond is much easier. Much easier to deal with. And that's why we continue to use it. We continue to use it because it is easy. And it's decently powerful. And, when we look at the electron density map, it doesn't look all that different. How many electrons does H2 have? It has a total of 2 electrons, right? If it has 2 electrons, each orbital can hold a max of 2 electrons. And so this one's going to be empty because it holds a max of 2 electrons. Now look at the density map here and compare it to the density map here. Do they look similar? Here's the 2 nuclei. Take a look at the electron cloud here and the electron cloud here. Do they look similar? They do. They look similar. And so sometimes there isn't that big of a difference. Sometimes there's a huge difference. We'll see. All right, so what we're going to do is we're first going to apply valence bond theory. Let's do that. In order to apply valence bond theory, number one, you have to have a Lewis structure. Valence bond theory and Lewis structure, same thing. You need a Lewis structure. Two, determine hybridization, if any. The way we determine hybridization is, for each atom, we look at how many groups of electrons. And so number of groups of electrons. I should make a slide for this. If we have two groups of electrons, it's going to be sp hybridized. If we have three groups, it's going to be sp2. If we have four groups, it will be sp3. If we have five groups, it's sp3d. And six groups will be sp3d2. Three. Going to determine the number of electrons. Determining the number of electrons, you have to pay attention to formal charge. If the formal charge is 0, then the number is the same as the valence. If the formal charge is +1, then it's equal to the valence minus 1 electron. If it's +2, it's valence minus 2 electrons. If it's -1, valence electron plus an 1. If it's -2, plus 2 electrons here. So we look at the charge on each atom. Determine the number of electrons on each atom. On each atom in the structure. Four, we're going to draw the energy level diagram. And fill with electrons. 5, we're going to show the sharing of electrons and making a bond in the energy level diagram. So how should I say that? We draw the energy level diagram filled with electrons, and then we show how sharing, i.e. bonding, is I have to show this by example. Hard to explain, but show how sharing, i.e. bonding, is from accomplished from the perspective of each atom. I should type this on. 6. Sketch a drawing showing the orbitals how they're filled and how they overlap. All right, so let's do a couple of examples of this. I need to add one thing on 4 here. Note number of lone pairs must match Lewis structure. Sorry. So let's do the first one. Let's do ammonia. If I look at ammonia, I'm going to draw the 3D Lewis structure. The 3D Lewis structure, we'll put the lone pair here, this bond in the plane. That means the bond sticks out and the bond sticks in like this. This is it. All right, now when I look at this, what is the hybridization on nitrogen? How many groups of electrons does nitrogen have on? Let's just count it. Single bond, single bond, single bond, 3 plus lone pair, 4. 4 groups means this is sp3 hybridized. Nitrogen is sp3 hybridized, right? Then what do? We're going to determine the number of electrons. How many electrons does nitrogen have? How many electrons does nitrogen have? 1, 2, 3, 4, 5. Do you see that? It has 5 electrons that belong to it. In other words, what's the formal charge on nitrogen? 0. So you have 5 electrons. So 1, 2, 3, 4, 5. So if it's sp3 hybridized, then we have 4 sp3 orbitals like this. This is nitrogen. Let's write it up here. Actually, no, sorry. Let's write it down here. I need extra room there. And then I need to fill these. So nitrogen has 5 electrons. And so I'm going to fill these up. 1, 2, 3, 4. Now where does the 5th one go? Fifth one is going to pair. And so that's a lone pair. Does nitrogen have a lone pair? Yes. Nitrogen has a lone pair and 3 bonds. Now, what I mean by this, show how the sharing of electrons, i.e. the bonding. So what's going to happen is a hydrogen 1s is going to come in. I'll just call him S. A hydrogen S comes in. This is nitrogen sp3. And a hydrogen is going to come in and share an electron. Another hydrogen S orbital comes in and shares an electron. Another hydrogen S orbital comes in and shares an electron. So we're going to have that nitrogen bonded to 3 hydrogens, like this. And then we show that in a drawing. So I know an sp3 orbital looks like this, and this. So I'll just draw out my sp3 orbitals. In one of the sp3 orbitals, I have a lone pair, so I'll draw it out like this. And the remaining sp3 orbitals, I have 1 electron spin up, which I'll draw like that. It could be spin down too, it doesn't really matter. And then the hydrogens are going to come in. So this is sp3, 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 sp3. And the hydrogens come in like this. The hydrogen comes in here and bonds with the s orbital. And we have this. And so this is an s-sp3 overlap. We have 2 types of overlap that are observed. There's called sigma overlap, which is different than the MOs that I was talking about. It's related. What we do is we draw a line between the nuclei. And if the overlap happens along the internuclear axis, which is this green line here, then this is called a sigma bond. We call this an sp3 to show what orbitals are involved, sigma bond. And it's sigma because the overlap is on the internuclear axis. There's another type of overlap. The other type of overlap happens outside the internuclear axis. and that we call a pi bond. But this is a sigma bond. We'll talk about pi bonds in a little bit. And here's another hydrogen. This is a hydrogen S. And then back here, there's another hydrogen. And so altogether, we're going to form 3 sp3 sigma bonds. Now, when we look at the electron cloud is going to be more concentrated. Where the orbitals overlap, there's going to be higher density. And so this is what holds the nitrogen's more polar. And so the electron cloud is going to be distorted. In fact, this is be distorted towards nitrogen here. But you can see the green negative charge is what holds the two nuclei together. In other words, what we're going to see here is this. So this is going to be delta minus. These are delta plus, and delta plus. We can show that by showing a skewing of the electron cloud. The electron cloud is going to be skewed towards nitrogen. I'll just draw it on one. Okay, was that okay? Can you do that yourself? This is a polar molecule. If I add up all these, what we're going to see is there's going to be a net molecular dipole like this. That is, it's negative up here. And so if I looked at the electrostatic potential map would be red at the top here and more blue down here. Green, blue. Does that make sense? In fact, do you want? Actually, I had the electrostatic potential map of ammonia up, but basically, this is kind of what we're getting at. Wrong one, sorry. You know, an interesting thing happens. You know, positive terminals of batteries. What are positive terminal of a battery colored? Like the negative terminal of a battery is black or red, and a positive terminal of a battery is black or red. You guys know? The positive terminal of a battery is red. The negative terminal is black. And so sometimes people have a mental association with positive being red. I do. I always have a hard time with electrostatic potential maps. Because with electrostatic potential maps, I always want to think of the red as being positive. I never want to think of the red as being negative. To me, it's backwards because the batteries. I learned that long ago, right? However, in Petrucci, the electrostatic potential maps are red for positive or negative? Red's for negative. Right? So does that really matter? It doesn't really matter. It's just some arbitrary, somebody decided, somebody who liked red for negative decided they're going to make red for negative. The color is irrelevant, right? The problem is when people decide to switch it. Like in this case, somebody decided to switch the map. Do you see it? It's obvious they switched the map because take a look at ammonia. The hydrogens are red and the nitrogen is blue, which is wrong because the nitrogen should be sucking the electron cloud towards it and be red, and the hydrogen should be blue. Until you look at their scale. Fortunately, they put a scale. Look at this. I wish Petrucci would have done this too, then I don't have to flip it backwards in my head. I wish Petrucci would have done positive as red and negative as blue, but he didn't. He did positive as blue and negative as red. So unfortunately, be careful out there. This is why you never want to memorize things by things that are relative, like tables. What's at the top of the table? Who knows what's at the top of the table because it depends on who wrote the table. And so you need to memorize other things, And so immediately when I saw this, I thought, oh, this is wrong. This is wrong because this is not, Petrucci would have had this inverted, the colors. But does it really matter? It doesn't really matter. What you should be is you should be flexible enough to go, okay, that's fine. This to me is more logical, the coloring scheme. But since Petrucci had it the other way, we're going to memorize it the other way for now. But keep in mind that other people don't agree with that. And so, of course, in science, you got a lot of people, a lot of personalities, and a lot of ways of interpreting things. But anyway, here, electron clouds can be sucked towards nitrogen, and we've got this lone pair here as well. And so the cloud is being pulled up here, making this more red and this more blue. Okay. All right, how was that? Well, how this was, it wasn't that hard. It wasn't that hard, and we got kind of the electron cloud. We kind of mapped it out a little bit. Do you see how we mapped out the electron cloud? And that's the utility of this. We're going to get these potential maps by pencil and paper versus a very expensive software program. Okay, now I want you to do this. For me. So go ahead and give you this your valence bond analysis and see what you can come up with on pencil and paper for this ion.